Okay, so we have another little tutorial here about another important concept in Chapter 1 called significant figures. Significant figures in a nutshell are going to help us determine and really kind of keep track of in a fair way how precisely a measured value is known. Okay, when we talk about precision, we're talking about how exactly we're able to measure a value. So for instance, when you're in lab, maybe you're faced with a situation like this one where there's a dial and you have to make a reading. I mean, this could be on a meniscus, on some kind of fluid measuring device, or some sort of electronic device. It doesn't really matter, but there's a series of graduations, and they're labeled, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay? And let's say that your reading comes right here where this little blue line is. What should we report that reading as? Okay, what would be fair to report that reading? Well, the way I see it here, it looks like this blue line is between this big demarcation for number 5 and 6. Okay, so it's probably 5 something. Now, do I leave it just as 5? Do I round it up to 6? How should I go about making a measurement here? It turns out that when you're in lab making measurements, you're always allowed to make a best estimate of one and only one digit. So as I look at this, and I kind of try to eyeball it as close as I can, from my eye it looks like that blue line is halfway between the 5 and the 6. So I'm going to call that 5.5. Now, did I directly measure that last digit, or did I estimate it? I would argue I estimated that last digit, okay? And I'm allowed to estimate one and only one. So when I make this reading, this is what I would report, and I would be done. Would you think it is fair for me to write that the reading that I see here is clearly 5.3712592517178113 units? No, that doesn't make any sense. My eye is not good enough to tell, what the 13th or 15th decimal digit is, right? That's just nonsense. I've just made these numbers out of thin air, basically, okay? So we don't want to do that in the lab. We only want to estimate one digit. Now, likewise, when we're doing calculations based upon the data that we collect in lab, we don't want the answer of our computations to really outstate or overstate the precision with which the measurement was made. And that's why the rules for significant figures and honoring significant figures is really important for measurement science and measurement scientists in general. Because the precision of a number is also important, just like its value is important, okay? We don't want to overstate precision and give the idea that we've more exactly measured something than we have. In this case, obviously, writing all these digits beyond the decimal point might give someone the false impression that I was very, very, very precise in this measurement. In fact, I wasn't. I had to estimate my second digit, okay? One more bit of terminology here. From time to time, you may hear someone refer to the least significant digit. That's basically the one that's furthest right in the number. Here, that's the one that I estimated. It's the one that's least precisely known, the least significant digit. Okay? All right, so we need some rules, perhaps, to help guide us in terms of identifying how many significant figures are present in our numbers. And there are some pretty simple rules that we can learn about and then practice, okay? So in a number that you're given, which digits are significant and which are not significant, and how can you tell? Well, I've written 2 rules up on the board here that I think if you remember, you can actually, and apply correctly, you can use these 2 rules to basically get yourself through any situation where you have to identify numbers of sig figs, okay? First off, this is a simple rule. Any number that's not 0 is always significant. Any non-zero number is always significant, always counts as a significant digit. Zeros, though, are the tricky ones, okay? However, if you see a 0 that ends a number, and a decimal point is written or present in the number, that 0 or those zeros are significant. So if they end a number and a decimal point is present, both those things are true, they are significant. Okay? Another thing that I want you to know about significant digits and precision is that numbers which are considered exact have no uncertainty associated with them. These are typically counting numbers. Like, by definition, there are 10 millimeters in a centimeter. There's 26 letters in the alphabet, the English alphabet, okay? These are numbers that have absolutely no uncertainty whatsoever, no imprecision, and because of that, those counting numbers or those exact numbers never, ever, ever limit your precision. They never affect significant figures, okay? And we'll see that once we start working mathematical type problems in the next video. But what I wanted you to finish up this video is ask you how many significant figures are present in these numbers that are written up on the board. See if we can practice just identifying sig figs, which are significant, which are not, okay? So let's look at that first number then, 0.0030. Now, the first thing that I see is, okay, 3. That's good news. All non-zero numbers are significant, so that one's clearly significant. And my second rule tells me that zeros which end a number, and if the decimal point's present, are also significant. So this 0 ends the number. So to me, it looks like both of those values are indeed significant figures, okay? The next one, 0.1044. Any non-zero number, you know, going to be significant. What about the 0? Okay, well, the 0 is between two non-zero numbers, and in such a case, that's also significant if the 0 is between two non-zero numbers. So that's also considered significant 0. There's 4 sig figs in this number, okay? Now what about the next one, 53.069? The only question is whether this 0 is significant because all the others are, and it's between two non-zero numbers. So it's technically been measured. That's 5 sig figs, okay? The next one, D, 0.00004715, okay? Now the 0 is in front of the 4, so clearly these 4 digits are significant, okay? But those zeros which are in front of the 4 oftentimes are not considered significant, okay? The ones that are right here, because they don't end the number and they're not between two non-zero numbers. So if this was a 1, then they would be significant, but here it's a 0, so they're not between two non-zero numbers. They don't end the number, so they're not considered significant. So there's only 4 sig figs here, okay? Part E is 57,600. How many sig figs does that have? I argue that this one has 5, that they're all significant. The reason why is that decimal point that I placed right here at the end. That decimal point is extremely important, okay? If that decimal point was not there, that number would only have 3 significant figures, the 5, the 7, and the 6. But by placing the decimal point there, those zeros in the number and the decimal point's present, which means there's 5 sig figs. If you place the decimal point there, it's almost like what you mean to the person that you're trying to communicate the number to is that you've measured those last digits. You've actually measured them. So that's an indication of higher precision. Now in this last case, this one's only got the 2 sig figs, the 5 and the 3, because there's no decimal point at the end, okay? So hopefully this video has been useful in terms of figuring out how many sig figs are present in a number. These rules will generally help you. The only exception that I came across here when we worked this problem are these zeros which are in between non-zero numbers, like the zero is sandwiched between the 6 and the 3, any zero that's between non-zero numbers is always significant. Okay, so that one always counts. So keep that in mind. This will help you understand how many sig figs are present in any number.